Hello everyone and welcome to section 12.3. We're going to talk about geometric sequences and series. Previous lecture we talked about arithmetic sequences and series. Now the signature of a geometric series is like this. So for instance, let's say I have a sequence that looks like so: 5, 10, 20, 40 and so on. Notice each time I double the number, right? And just to make sure here, there is no common difference. The difference 10 and 5 is 5, 20 and 10 is 10, and that's 20. So there is no common difference. The reason I say that is because previous section, we talked about arithmetic sequences. We said the arithmetic sequences is right here. In an arithmetic sequence, there is a common or fixed difference. Well, the sequence I have right now is not arithmetic, correct? So there is no common difference. Therefore, this is not arithmetic. Now, the way I structured this one, because I'm multiplied by 2 to go from first to second, second to third, third to fourth, you each time multiply by 2. Okay, so this is what I call the signature of a geometric sequence. In general, this is how the arithmetic sequence works. In order to go to the next term, a sub n, you multiply the previous term by a fixed number r, which is called a common ratio now, to get from one term to the next term. And this is again the recursive definition. Okay, that will be the recursive definition of a geometric sequence. Now, the reason it's called common ratio is this. In my example, if you take the ratio of second to first, it will be exactly the same as third. Third is 20. To second, exactly the same as the ratio of fourth to third. All of these ratios are the same and hence a common ratio. But when we write it, we usually write it in the way you see it in a recursive formula. A sub n is when you multiply a previous term by a common ratio r. In order to find a common ratio, by the way, usually we divide second by first term, and that will give us a working common ratio. All right. Now, what is the functional form? F of n is what? Which is, remember, a sub n. We just want to write it in as a function. Okay, as a formula, if you will. The recursion doesn't give us a formula. It just gives us a working formula, but it doesn't give us a functional form. Let's do this. For example, suppose my a sub n is given by, I'm giving you the function now, 2 to the n minus 1 over 4. Okay, and we want to write the first few terms, but first let's do this. Let's say we want to show that a sub n is a geometric sequence. Okay, to show that it's geometric, we need to show the common ratio is a constant. So the common ratio, for that we go a sub n divided by the previous one. Or you can go next one, a sub n plus 1 divided by a sub n, as long as you have two back-to-back terms. Now, a sub n here is 2 to the n minus 1 over 4 divided by the previous term is going to be 2 to the n, but then previous to n is n minus 1, right? Minus 1 over 4. See, right in here, I changed n to n minus 1 for the previous term. All right, the 4's cancel, so I have 2 to the n minus 1 divided by 2 to the n minus 2. True? 2 to the n minus 2. And let's see, for this one, I can actually work this now. Using the properties of exponents, I can write it as negative n plus 2. I'm using this rule of exponents. A to the m over a to the n is a to the m minus n. That's what I'm using. So n becomes negative n, negative 2 becomes 2. And when I do this, I get, let's see, 2. Yep, so I'm going to get 2 to the first, right, which is 2. So the common ratio is going to be 2. And because it's a constant, therefore, there you go, it's a constant. And we just prove that this sequence is, so the sequence, so a sub n is geometric. There you go. Now, if we wanted to, we can find any terms. So just let's write out the first few terms. How's that? A sub 1, that's when n is 1. 2 to 1 minus 1/4, that's 2 to 0. 2 to 0 is 1, so the first term is 1/4. What is the second term? Well, that's 2 to 2 minus 1/4. 2 minus 1 is 1, so that's 2/4, which is 1/2. Notice, half is twice 1/4. So the common ratio is 2. And from this, I can get all the subsequent one, right? If you want, just to do one more, a to the a sub 3 is 2 cubed minus 1/4, which is 2 squared over 4, or 1. But then I can use the common ratio to go from one term to the next and the next and the next. So the next one, double that, you get 2, double that, 4, 8. There you go. We can get to the terms faster. And again, this is the using the recursion, what I just did here. When you multiply previous term by a common ratio, I just did that. I use a recursive way of listing them, but we did have a formula, a function for this example. Now, what if I want to find a formula for the nth term? How about that? A formula for nth term, which I call the functional form of the series. Well, it'll be relatively easy to derive this. If the first term is a, remember, to get to the second term, we multiply previous term times a common ratio. So that's just going to be RA. True? Well, let me keep it as a sub 1. What about the next term? We'll do R times A2. But then A2 was RA1. That's R squared A1. And let's do A4. A4 is the previous term times common ratio. Previous one is R squared A 1 times R, so that's R cubed A sub 1. And now we can see a pattern. See, when the subscript is n, in this case 4, the exponent on R is 3. So we can state, this way I can state the nth term in terms of the first term and the common ratio. And this would be the functional form. Okay, and one thing, by the way, when we go back here, the common ratio here, R, cannot be 0. And you can see, for obvious reason, if R is 0, then everything is 0. So we really don't have a geometric sequence. And there you have it. This is the general form. Again, this is the functional form, I call it. This is the functional form, means written as a function. Let's try some examples, see how it works. Suppose my first term is square root of 3, and I'm going to make my common ratio to be the same. Okay, and what do we want to do? Let's say we want to find the general term, and we want to find the fifth term, something reasonable. Well, the general term, a sub n, is a1 r to the n minus 1, correct? And n here again is a natural number. Remember, that's 1, 2, 3, 4, 5, like that. So I can do a sub 1 root 3 times common ratio is root 3 to n minus 1. Now root 3 is root 3 to the first power. I can actually multiply using product rule of exponents. A to the m, a to the n, you add the exponents, right? So I can use that to write this as root 3 to 1 plus n minus 1, or simply root 3 to the nth power. And that's going to be the general term. That means I can produce any term I like. I can find the 5th term, 50th term, or 5,000th or 5 billionth term in the sequence. You just change n with your desired number. So I want to know what is a sub 5. I'm just going to plug in 5 for n here, a sub 5. Cool. And square root of 3 to the 5th, well, that's like square root of 3 to the 4th times square root of 3, right? And square root of 3 to the 4th, that's root 3, root 3, root 3, like that. That's going to be 9 root 3. Or you can just list square root of 3, but that's how you can do it. Or I can go write root 3 to the 4th as 3 to a half to the 4th. So this is more of algebraic method, right? Using properties of exponents, you get the same results. So however you do it. And there we have it. That's going to be an example of geometric sequence. Let's do another example. Let's say this time I'm going to give you a sequence 1, 1/2, 1/4, and so on. Okay, and suppose we want to find the 7th term. Find a sub 7. Now we want to use a formula, by the way, to do it. You could count your way to the 7th term, but let's use the formula. Now, I need to find a common ratio, right? Common ratio, a couple of ways you can do this. You can divide 2nd term by 1st term, or you can do 3rd by 2nd, as long as you divide 2 successive terms. Now remember, again, division is not commutative, so it makes a difference if you do 1/2. You don't do 1st by 2nd. You have to do 2nd by 1st term. Okay? And when you do that, you're going to get your common ratio. That's one way to do it. Or try to figure out how you go from 1st to 2nd term, from 2nd to 3rd, and so on. For example, to go from 1 to 1/2 through multiplication, I have to multiply by 1/2, right? This is going to be my common ratio. Again, to go from a half to a quarter, you multiply by 1/2. See that? So 2 ways you can do this. However you do it, the nth term, 1st term, r to the n minus 1. Therefore, the 7th term of the sequence is going to be 1st term is 1. Common ratio is 1/2. And 7 minus 1 is 6. So that's 1/2 to the 6th power, which is 1/2 to the 6th power. And 2 to the 6th power is 64. And that's going to be the 7th term in my sequence. Pretty simple. Let's do another one. Let's say I want to find, and this time I want to find the nth term. Not a fixed term, like 7th term. I want to find the functional form, if you will. Okay, so how am I going to do this? Again, we have a formula for it, right? Suppose that's my sequence, and the formula we had was up here. This is the formula I'm going to use. I need to define, or I need to find my common ratio, or divide 2nd by 1st term. You get your common ratio. What is the 1st term? -3. And here's the formula for the general term. A sub n is a sub 1 r to the n minus 1. Because it's general, n is going to be in our final answer. 1st term was -3, and r was -1/3 to the n minus 1. So this is an acceptable answer, but we could, because I see the 3's here, we could manipulate this further. And how are we going to manipulate it? Let me show you the manipulated version. For lack of a better word, we're going to manipulate it. That's my -3, right? -1/3 in parentheses, I can write it as -1 let me keep it like that. Yeah, let me write it as negative 1 to the n minus 1 over 3 to the n minus 1. All right, now let's work these. I'm going to work the negative 1 with negative 1 to the n minus 1. Well, negative 1 is negative 1 to the first power. Using the product rule of exponents, that's negative 1 to n to the n power, correct? And 3. Well, 3 to the first power divided by 3 to the n minus 1. That can be written as 3 to the n minus 1. Bring 3 to the first power to the denominator, becomes minus 1. So that's now 3 to the n minus 2. So this is one way to write the answer. Okay. Or another way I can do this is the following. This is acceptable. Okay, or I can do it this way. I can write negative 1 to the n and multiply by negative 1 to the negative 2 power, negative 2 exponent. That's still 1, right? I'm multiplying the top by 1 by doing that. And why am I doing this? So this way I have negative 1 to the n minus 2 over 3 to the n minus 2. Now we can combine these two into one expression. Again, these are different ways you can see the answer. All three are acceptable. Okay, depending on how you want to show the answer. I'm okay with all three of them. Okay. Cool, done with this one. Now let's take a look at the nth partial sum. S sub n, which is what we call the nth partial sum of geometric series. The nth partial sum, again by definition, that's when you add the first few terms of a sequence, right? And there you go, that's what the nth partial sum is. Now, for geometric, here's A1. Remember, A2 is when you multiply A1 by R. A3, multiply second term by R. And all the way up to the last one, A1, R to the n minus 1. Right? Which we can write it in sigma notation, by the way. I can write it as K1 to n of A sub 1, because the A sub 1s aren't changing. But the R's are changing. Right? R's are going from 0 exponent here, A1, R to 0 is A1. So there you have it. R goes from 0, 1, 2, and there you go. This will pick it up. So I can write it in sigma notation the way you're looking at it. That's going to be the nth partial sum. Now, I actually want a formula for it. We don't want this way. We don't want the sigma notation. So what am I going to do? I'm going to multiply both sides of this equation by R. Okay, let's multiply by R. So when I multiply by R, I get R times S sub n equal. Now, every one of these terms gets multiplied by R, correct? Therefore, the first term is going to be what? It's going to be R, and it's going to be A sub 1 plus A1. The next one is going to be R squared. Next one, R cubed. All the way up to the last one is going to be what? A sub 1 R to the n minus 1 times R. And that's going to be just A1 R to the n. Correct? And then let's subtract. We're going to subtract the bottom from the top. Okay, in other words, when I subtract the bottom from the top. So I'm going to write the top first. Negative R S sub n second. That's subtracting the bottom from the top. Now, in the way it works with the A's, I have A1, A1R, a1r squared plus, let me go one more, a1r cubed plus dot 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 plus a1r to the n minus 1. And from this, we're subtracting all of these minus r a sub 1 plus a1r squared plus a1r cubed. You see how that goes. All the way up to plus a1r to the n. And as you can see, when we subtract, we're going to have all the in-between terms canceling. In fact, even this term will cancel with the same term that with the previous term to a sub 1 r to the n of the next series. So all said and done, I'm going to get a sub 1 plus a sub 1 r to the n. I'm sorry, minus. And the reason, because we are subtracting, minus. So it's going to be minus. And almost done. On the left, we can factor the nth term, partial nth partial sum, s sub n. We get 1 minus r. And on the right side, I can factor a sub 1. And from this, the nth partial sum is going to be a1, 1 minus r to the n, divide by the coefficient on the left, or 1 minus r. And we have our formula. Okay, and this is the formula for the nth partial sum of a geometric series. The conditions are cannot be 0 or 1 in this case, because you get division by 0 if you use it this way. All right, and there you have it. That is the formula we're going to use. Let's do an example right away. How do I use this formula? So let's say we want to find the sum. And s sub n, I'm going to make it to be, let's say we make it to be 1/4 plus 2/4 plus 2 squared over 4 plus 2 cubed over 4, and so on all the way to the n minus 1 over 4. Okay, we want to find the n partial sum. Now, because I don't know what n is, right? Because it ends with nth term, we're not going to get a number out of this. We're going to get an expression. It's geometrics. A1 is 1/4. The common ratio, remember the common ratio is, to find the common ratio, you divide the second term by the first term. And that's 2. Or you can say, well, how can I go from 1/4 to 2/4 is a half. You multiply by a half to get there. However you think of it. The common ratio is 2. And we need both of those in order to do the formula for the nth partial sum. Now I'm going to do this formula. Okay. S sub n is going to be a1, which is 1/4 times. In the numerator, we have 1 minus, common ratio is 2 to the n, divided by 1 minus 2. 1 minus r. Correct? And 1 minus 2 is -1. I'm going to put the -1 in front of the fraction. That will make it -1/4. And 1 minus 2 to the n in the numerator multiplies by that. And there you go. And that is what the nth partial sum is. So I can say, well, what if I add the first 500 terms of this series? I can get the answer using this formula. All right. And there we have that one. Let's take a look at one more example here. So in this next example now, I'm going to do, let's say, sum k goes from 1 to n of 4 times 3 to k minus 1. Now this has the structure that you see. I'm writing a1r to the n minus 1, or see? It has exactly the same structure. And again, some people actually write this out and determine first term and common ratio using the series. I like to match them against the form. Here's how those other people do it. They say, well, k is 1, so this is 4 times 3 to 0. Next term is 4 times 3 to k is 2, plus so on and so forth. So this would be 12 plus, I'm sorry, not 12. 3 to 0 is 1. 4 plus 12 plus dot, dot, dot. All right, so here's my first term. And the common ratio, you do 12 divided by 4, you get 3. Well, I can get it in the way I'm doing it. First term is 4. And the common ratio is 3. Just matching it against the general form. So however you do it, we're going to now be able to find the nth partial sum, S sub n is equal to, and I'm doing this formula. First term times within parentheses. So first term is going to be 4 times 1 minus r to the n over 1 minus r. 1 minus 3 is negative 2. 4 divided by negative 2 is negative 2 times 1 minus 3 to the n. And again, this would be the general formula for the sum of any number of terms in the sequence, or I'm sorry, in the series. Okay. And now we're going to finish this section with our next very interesting idea. Let's talk about convergence and divergence of geometric series. Convergence / divergence of geometric series. And to do this, I'm going to actually look at some examples first, and then we'll generalize this, okay? Now, for example, one thing about the common ratio, by the way, r, I'm going to let r be 1/5. And then we're going to look at powers of r. So r squared is going to be 1/25, r cubed 1 over 125, and so on and so forth, right? Now, one thing we can immediately note here is that when you raise r to a power, in this case 1/5, the fraction is getting smaller, isn't it? Like 1/5 is greater than 1/25, 1/25 greater than 125th, and so on. Or we can say the other way, we can say that 1/25 is less than. Is going to be this way. There you go. 1/25 is less than 1/5. And we can go in this direction now. 125th less than that, 1 over 625th less than that. But the point being, it looks like the fraction is getting smaller and smaller. So as n, imagine now if I have r to the 10th, to 100, to 1,000 power, what's going to happen to this one? So for instance, if I go r to the 10th power, look at this one. That's going to be 1 over 5 to the 10th, which is almost 0, isn't it? So we can generalize this then. We can say that in a note. If absolute value of the common ratio is less than 1. Absolute value, because the common ratio could be negative, for example. If the common ratio is a negative, by the way, that would generate alternating geometric series. One that alternates between plus, minus, or minus, plus, like that. But however it works, if absolute value of common ratio is less than 1, then r to the n, we say, approaches 0 as n approaches infinity. Means as n gets larger and larger. Now, this is actually, it has a very interesting consequence on the formula for the nth partial sum. If you remember the nth partial sum formula, we just worked with it. It was this one, right? Well, if absolute value of r is less than 1, we just said r to the n approaches 0, right? Means this portion goes to 0. Therefore, s, and I'm going to change n with infinity now because it's a limiting process. As n approaches infinity, the sum to infinity is what we call this. Sum to infinity. can be written and exist as a1 over 1 minus r. Because in the numerator, we just have 1, right? a1 multiplies by it. And look at how simple this formula is. Actually easier than the formula for the nth partial sum itself. So, making a long story short, it is possible for us to find a sum to infinity of geometric series, those whose absolute value of common ratio is less than 1. This is very interesting, and it has far-reaching consequences in our work. Later on, you work with these in your calculus courses, and you'll see what I mean. Now, what happens here, by the way, we say that the series, in this case, we say the series converges. If absolute value of r is less than 1, the series converges. If absolute value of r is 1 or more, the series diverges. Okay, let me write that. If absolute value of r greater than or equal 1, the sum to infinity diverges. Means it gets too big. It doesn't come to a point. We cannot find the sum. So let's take a look at just a few examples here, and we'll wrap it up. For this example, let's say I'm given this series 1 plus a third plus a ninth and so on. And the question, we want to determine whether this series converges or diverges, and if it converges, we will find its sum. So I need to find common ratio, which is second term by first term, 1/3. Absolute value of 1/3 is less than 1. Therefore, series converges. That's all we need to do. Just find r. It converges. Well, now if it converges, we like to be able to find the sum to infinity. The sum, which some call it the limit of the series. The sum is going to be first term over 1 minus common ratio. First term 1. 1 minus 1/3 is 2/3. Invert and multiply, we get 3/2. The sum is going to be 3/2. Isn't that fascinating? Means if you add all of these to infinity forever, if you add them forever, the sum would be 3/2. It will be very extremely close to 3/2. Okay. Now, what's interesting to me, what's fascinating, is how fast this thing converges. If you look at just the first 3 terms here, you look at 1 plus 1/3 plus 1/9. Well, 1/3 is 0.33. 1/9 is a third of that, 0.11. So if you look at just the sum of the first 3 terms, it's about 1.444, right? 3/2 is exactly 1.5, and look at that. Beyond the third term, from 4 to infinity, you're adding about 0.06 to this sum. The fact that the convergence is so rapidly makes these geometric series very useful, and they're often used in approximating other function values. Okay, but it does require absolute value of common ratio to be less than 1. Okay, and there you have that one. I just want to show you the lion's share of that 1.5 is captured by just the first 3 terms. You go up to the 5th, 6th term, you're almost going to be at 1.5 already. Okay, now let's try another example. Okay, in this example, I'm going to use the sigma notation for the series now. Let's say we want to see whether the sum of this geometric series converges or diverges. Notice I have sum to infinity. Okay, all the nth partial sums converge. It's just the infinite sums that may converge or diverge. I need to find the common ratio. Again, this is my first term. Common ratio is 3. Absolute value of 3 is greater than 1. Therefore, the sum diverges. We're done with this one. We cannot find the sum. It gets to be too large, too big. So we cannot find this sum. Well, let's do another one. And this time, suppose I want to do the sum from 1 to infinity of 6 times negative 2/3 to k minus 1. First term is 6. Common ratio is negative 2/3. And again, the reason because I'm matching it against this form. Right? This is the nth term of a geometric series against that. So for this one, absolute value of negative 2/3, see, r can be negative, and it is in this case. It's going to be 2/3, which is less than 1, therefore the sum converges. Now, if it converges, we want to find the sum. So what is the sum to infinity? It's very simple. First term divided by 1 minus common ratio. And the first term is 6 divided by 1 minus, common ratio is negative 2/3. Make sure you keep it as it is. We only use absolute value of r to determine the convergence or divergence of the series. Now, 1 minus 2/3, that's 1 plus 2/3, that's 1 2/3 or 5/3. Invert and multiply 5/3, we get 3/5. And 6 times 3/5, that's going to be 18/5. Okay, and there is your total. 18/5, which you can divide 15 by 5, so that's 3 3/5. I left it as an improper fraction. You can write it as a mixed number like that. And that's about 3, not about, but it's exactly 3.6. That is what the sum is. Okay. Well, let's do maybe one more, then I'll do an application, an interesting application of this one. Let's say I want to do, suppose I have sigma of 3 times 2/3 to the k now. K is 1 to infinity. Now you got to be careful here because the exponent is k. Remember the general term I had up here. If k starts from 1, then the exponent, oops, sorry, I messed this up. It's not n. This should be k. I'm sure many of you caught this one. I'm glad I went back. There you go. That's the in sigma notation, or in the sigma notation. So it has to be k minus 1, the exponent on common ratio, when k is 1. I have k in here, so I need to work this a little bit. And how do we work it? Well, let's actually write this as following. We're going to write the... Here's what I want to do. In order to create k minus 1, the different ways you can do it. You can write it out and create your own series that with k minus 1. But because I need k minus 1, easy way for me is to do this. I'm going to do 2/3 to the first power and to negative 1. This product is 2/3 to 1 minus 1, 2/3 to 0, which is 1. So I haven't really changed anything by doing this, right? Now, why would I want to do this? Because the exponent has to be k minus 1. That's why. I'm going to multiply 3 times 2/3 together. And now I can combine these two together. Bases are common, you add exponents. So that's going to give me 2/3 to k minus 1. Okay. And finally, 3 times 2/3, that's just 2. So I can write this as k1 to infinity of 2 times 2/3 to k minus 1. So I had to manipulate it in order to make sure it looks correctly like the formula above. Now it does. When it does, this is going to be first term. That's going to be the common ratio. True? Did I have to do it this way? No. Again, you're welcome to write out the series. Try K1, K2, and then you'll see that it works. Now, common ratio, absolute value of 2/3 is less than 1. Therefore, the sum converges. The series converges. The sum to infinity is A1 over 1 minus R First term is going to be 2. 1 minus common ratio of 2/3. That's 2 over 1/3. Invert and multiply. We get 6. The sum is going to be 6. All right. So we're done with this one. If you want to write the series out when k is 1, 3 times 2/3 to the first power. When k is 2, 2/3 squared. That's this one. And so on and so forth. So you get 2 plus 3 times 4/9. That's plus dot dot dot. That's 2 plus 4/3 plus dot dot dot. The common ratio, you divide 4/3 by 2. And to divide by 2 is to multiply by half. And there's your 2/3. Right? Exactly like I have it. So that would be your really other alternative, is to actually write the series out in order to get to the same numbers that I got. But nonetheless, it can be done. If that's what you want to do, that's fine. Okay, now let's finish this with an application. So I'm going to bring in the application and then we'll finish this work. And here it is. In this example, the classical example, by the way, the number of grains of wheat on a chessboard. So the problem reads, in an old fable, a commoner who had saved the king's life was told he could ask the king for any just reward. Being a shrewd man, the commoner said, "A simple wish, sire. Place 1 grain of wheat on the first square of the chessboard, 2 grains on the second square, 4 grains on the third square, continuing until you have filled the board. This is all I seek. Compute the total number of grains needed to do this to see why the request, seemingly simple, could not be granted." Now we were told that this is an 8x8 chess board, typical chess board. So the way this works is 1 grain on the first square, 2 on the second, doubling each time, right? So the sequence is a geometric sequence because there is a common ratio of 2 here. First term 1, common ratio 2. So what I did here for you, I went ahead and plugged these numbers into our formula for the nth partial sum. And check this out. All said and done, the number is huge. Ends up that the king needs to offer this commoner 18,400,000 trillion grains of wheat in order to reward him, and that is not practical. Therefore, I guess he's not going to be rewarded. So here you go, just a simple, interesting application of geometric series. So with that, we are done with this lecture, and I hope you find it easy to follow. And geometric series are very important in our future work, in our other courses. And for now, we are done with this lecture. As always, thank you for being here and thank you for watching. Hope to have you in another video. Take care and goodbye.